So I'm pretty excited about today's class. You know, there's a cyclone about to hit the East Coast, but this is pretty cool too, okay? Yeah. I actually think this is one of the best topics of this entire course, okay? And I'll show you why in a minute. So let's just refresh our memory though. And I'm sorry this keeps blinking, but I don't know what's going on with that. So, last time we introduced a new operator called the del operator. Nothing to do with Tisdell operator, but it looked like this. Oh, 1L actually, but anyway, that's fine. It was called the del operator, and it has sort of partial derivative operators in it. You can think of it as a vector, and we applied it to functions of 2 and 3 variables. And we worked out that geometrically you can talk about the resultant vector being normal to the level curves and the level surfaces. And we also looked at the idea of a directional derivative. Okay? Now, a directional derivative, just to refresh everyone's memory, is the slope of a tangent. So let me show you. Right? You start off with something like that. Yep, you've got a surface, and you've got a point on the surface, and you've got a vector that points in some direction. Okay? And the idea is to understand the slope of the surface at that point in the direction of the vector. So what do? You find a plane that contains the point and is parallel to the given vector. Okay, that smashes into the surface and you get a curve. Yeah? What the directional derivative does is it tells you the slope of the tangent line to that curve at that point. Okay? That's what it does. That's what it does. All right, so it's no real different from partial derivatives, from the derivatives that you learnt at school, because it's still the slope of a tangent line. And the question is, well, which tangent line? This one's a pretty crazy one, right? So that's what we did last time. In today's lecture, we're going to look at what we can do with this del operator a bit more, okay? So before we go any further, remember vectors. Vectors from 1, 1, 3, 1. Okay? Take me back to 1, 1, 3, 1. Yeah? So how can we combine vectors? How can we combine two vectors? What are some of the ways? Who can tell me? Some of the operations. Cross product, right? So we cross one vector with another vector. What else?
Dot products.
Yeah, dot products. What else can we do? Scalar multiples. Yep, you can stretch them, you can flip them, you can compress them, you can add them, you can subtract them, all that sort of good stuff, right? So, yes?
Scalar triple product.
Scalar triple product. Exactly. God, nightmares, right? Yeah, it's cool though. Now, what we're going to do is we're going to look at some of those things in today's lecture with this operator. So try to think about what happens if you cross this del thing with a vector. What would you get? Okay? Well, let's think back to first year. If you cross two vectors together, cross product, what's your output? What do you actually get out of it in a general sense? Yeah, it gives you a vector that points in a certain direction, right? What about the scalar product or the dot product of two vectors?
If it's 0, then that means the two vectors are like perpendicular.
Yep. And so 0, so let me concentrate on that for a second. The output's a number. If you take the dot product of two things, you get a number, not a vector. Whereas if you do the cross product, you get a vector, right? Do you think it's going to be the same with this? Yes. Okay, yes. So let's look at two things. Let's look at two things. Okay, the first thing we're going to look at is called the divergence. Okay, the divergence. So let's just remind ourselves. This operator is defined in the following way. Now, divergence is a bit of a strange word. It sort of means, I guess, in a loose sense, to move away, to diverge from something, right? But the way I think of it is called spread. Okay? All right. So here, who's doing fluid dynamics here at the moment? Okay. Do you recognize this word, divergence, yet? Who does? Yes, maybe? What? So, you heard about it. That's okay. That's okay. You heard about it, right? So you'd be talking about fluids, right? Have you heard of incompressible fluid? Yes. Okay. So incompressible fluid. So water, I think, is an incompressible fluid, right? What does that mean? It means that if you put the fluid under pressure, it doesn't expand or contract. Okay? So the tendency to spread, well, there is no tendency to spread, right? It's incompressible. It doesn't want to sort of shrink or grow. Okay? All right. So let's just see what this actual divergence thing is, and then we'll talk about it. Okay? So let's look at a couple of examples. Now, the reason why I keep writing this out again and again and again is because you don't need to memorize divergence, curl, whatever we'll look at today. If you just remember that little triangle, that's pretty much all you need to know, as long as you understand the dot scalar operation or the cross, the curl operation. Okay? So let's just have a look. Here is something that looks like a function, but the output is a vector. Okay? We haven't seen anything like this yet. Okay? So this big F, it's got boldface, implying that it's a vector. It's got three components, an I component, x squared minus y, a j component, y plus z, and a k component, z squared minus x. So you put in x, y, z, it'll output a vector, not a number, a vector. Okay, it's called a vector field. Okay, it's like a function, but it outputs vectors. Okay, same with this one, this g. The g here would be 0i plus xj, where I and j are the unit vectors. So if you vary x, your j vector is going to vary as well. Okay? All right. Let's have a look. So we use two kinds of notation. The first notation we use is div, and the second notation is the dot notation. Okay? So if I'm unsure of this, I basically just write it out as two vectors. Yeah? So if I can't remember what's going on, I can always write it out longhand. Okay? Okay? So, can anyone remember how we do a dot product or a scalar product in a product? I've forgotten. Can anyone remember? Huh? It's not a trick question.
You just multiply the corresponding sort of x, y, z of the two vectors.
So normally we would multiply, right? So what are we doing differently here? Same sort of principle. We're operating. So it's like you're multiplying, but you're actually taking the ddx of that plus ddy of that plus ddz of that. So for everyone at home, ddx of that plus ddy of that plus ddz of that. That's what you're meaning, I'm sure. Yeah. Okay? All right, so again, this is using partial derivatives, which we saw in the very, very first lecture. Okay, so ddx of that will be what? 2x. Yeah? Oh, it's not going to be a vector. Ddy of that's going to be 1. ddz of that's going to be 2z. Okay? So, our answer is not a vector, it's going to be a number. We don't know what it is yet, we don't know what it means, but I'm telling you now, it has something to do with the spread of a vector field. Okay, the sort of compression or expansion is another way of looking at it. Okay? All right, let's compute the divergence at the point of interest. So let's call this P. So it'll be 2 times 1 plus 1 plus 6, 9. Okay, so it's just a number. Okay, part B is much more interesting though. Okay, part B is much more interesting because it sort of tells you a little bit about what the divergence calculates. Okay. Before we get on to that, questions? Questions. If you can do a dot product, it's pretty easy, right? And you can differentiate. It's pretty easy. Yes, sir.
You mentioned, it's a very minor thing. You mentioned operating earlier. What was the difference between that?
I'm like the del vector. It's like an operator. You can because you're not technically you're not multiplying. You're not. You know, the only thing you're doing is operating the derivative. You're saying, hey, I'm going to take this and differentiate it. I'm going to take that and differentiate it. Okay? Yeah. Other questions? Yes.
Just to clarify, you're doing the dot product of the gradient and the vector field. Is that, or is it not?
No, that's a really good question though. What has this got to do with gradient? Nothing. No, because f is a vector. It's not like a function of 2 variables or 3 variables, which gives us a surface or something like that. So the dot is super important. The notation is super important because even I get confused. Sometimes I'll look at something and I go, oh, that's the gradient. And then I'll look closer, oh, there's a dot in there, right? So the notation really matters for this sort of stuff. Just like, I'm very pedantic, I'm very careful about putting these squiggles under the F. Why? Because I'm telling you it's a vector. Okay? If it wasn't there, it would be different. Okay? Does it make sense? Yeah. So the only really thing that's related to gradient is the operator itself and not the dot. Yeah. Okay. Let's look at B. B's a far more interesting question than part A. If G is that, and that's a vector field, compute the divergence of G. Sketch G, now this is where it gets interesting. sketch G and show there is a net zero outflow over each rectangle. So you can think of G as like a velocity of a fluid. Okay? So fluid's moving around. We've got a way of describing it using this vector G. And depending on what point we are, the velocity will change. Okay? So if I was sort of carefully looking at this, I could write it like this, or I could write it like this. Remember, I and J are just the unit vectors. Okay? So what happens to the length of G as x increases? Here's a good question. What happens to the length of G as x increases? Can anyone predict? As x increases. Doesn't stay the same. Because what happens if x equals 1? What's the vector G? Yeah, it's going to increase. It's going to increase, right? So if you're at the point, I don't know, let's say you're here. You're at the point 1, 1. Yeah? X equals 1, y equals 1. What is the vector associated with this field? Well, it'll just be 1j. Okay? Whereas if I'm over here, let's say I'm here on the negative axis. Let's say I'm here at, I don't know, -2. That'll be negative 2j. Okay? So as you move around, we're only in the plane here. As you move around, this vector field, the vectors are going to change. But who can tell me what doesn't change about this particular vector field? The length changes, but what kind of stays the same? What kind of stays the same? Yes. Sort of, yeah. If x is positive, all the arrows are pointing up. If x is negative, they're all pointing down, and they're parallel to the y-axis. Yeah. So you're right. You're right. Okay. So let's compute the divergence, and then we can kind of explain it, if that makes sense. All right. For this one, we're only in 2 dimensions, so we can just do this. Okay, ddx of 0 is going to be 0. ddy of x, 0. So, in this case, we get an answer of 0. And it doesn't matter where we are, the answer is still 0. So, this is what we call the characteristic of an incompressible fluid. Okay, an incompressible fluid. So let me explain that a little bit more, where we sketch G and show there is a 0 net outflow over each rectangle. Okay? Oh, this is good. I'm going to come back to that. Okay, so let's just sketch. Okay? Now, man, it just doesn't like do what I want to do, hey? Okay. Yeah. All right. Now imagine that's my rectangle. And as x increases along the positive axis, my arrows are going to get longer and stick straight up. Okay? So say I'm here, my arrows are going to stick straight up. If I'm over here, they're going to stick straight down. Okay, it isn't a great rectangle, but you get the idea. If I'm here, it's going to stick up, but not quite as much. Okay? What about if I'm up here, say? If I'm down here, right, from here. Okay. Now look carefully at the boundary, just the edge, the perimeter. Okay. Who can explain to me why there's a zero net outflow over such a rectangle? Who can tell me? Hang on. Just from the picture. Just from the picture.
The vectors are equal and opposite, so they cancel each other out.
Yeah. Is that what you're going to say? Yeah. So, if you look, say, along this edge, just this part here, there's definitely fluid flowing into the rectangle or the square or whatever it is, right? But the same amount of fluid is being expelled. Yeah? Look at this edge. It's entering, but also being expelled at the same rate. Okay? So overall, we would call that situation a zero net outflow. Overall, there's nothing, leaving. Oh my God, just work. Thank you. Okay? So, questions? Has anybody seen anything like this before? I'd be very interested to know. Yeah, where have you seen it? Oh yeah. Hang on. Yes.
If the vector function is 0x,
Yeah.
won't all the vectors be along the y-axis since the x component is always 0?
No, well, it's just think about 0I plus xj. Which direction does the j vector point in, right? And if it's negative, it points down. Yeah, but they're tricky, right? This is not a difficult function, the g, right? But I'm saying it's not tricky. It is tricky. It's difficult, especially if you haven't seen anything like this before, right? I mean, who in hell knows what that looks like? Like, that's horrendous. But that, maybe if we try hard and think, we can have some idea of what it represents. Okay? You stupid. Other questions? I sent an email to IT, the AV people, about 2 weeks ago. They closed my ticket today saying, everything's fine. You are my witnesses. Everything's not fine. Do we agree?
Oh, could you explain where the rectangle comes from? Is it the function?
No, I'm just drawing it. I'm just drawing it. So basically I want to show you that for this kind of, it doesn't have to represent anything, right? The important thing is, it's a two-dimensional thing that's got a boundary, right? And sometimes what we like to do with fluids is we like to measure the flux across the boundary, or the flux that goes in and out of something, okay? Like it could be a membrane, or it could be lots of things, okay? I've just tried to choose the simplest shape. I'll choose a circle in a minute, right? Just the simplest shape that sort of suits this problem. Okay, so it doesn't come from the problem. I've just said draw a rectangle, and I've centered it at 0 at the origin. More questions. Let's have a look online at home. Oh, hang on, I'll just go. You stupid. All right, can you please explain why no outflow? Everything that goes through this edge that flows out also flows in at the same amount. Same here. Everything that flows out of there is replaced by everything that flows in there. Okay? That's what I mean. Okay, questions? Cross product, the most normal operation. I like it. I like it. That is great. Keep it up. I do like puns. Am I correct to say that this is the dot product between del of f? It's just del of f. It's the dot product between the del operator and the vector function, or the vector field. Okay? Yeah. What else have we got? So, with the divergence function, it is in a way referring to the sum of the outputs. Yeah. You could think of it that way. You could think of it that way. And then the question is, well, what happens if your answers say positive? Right? Like you compute the divergence and you get a positive answer. Can anybody hypothesize? You compute this del thing, you get positive 2. Can anyone hypothesize what it might mean? Anyone? Anyone at home?
There's a positive net flow, so more liquid is leaving.
Yeah. So, if more liquid or whatever substance, whatever it is leaving, what is the vector field doing? It's spreading. It's expanding. Right? It's expanding. This is sort of neither expanding or contracting. Okay? And if the divergence is negative at a point, you draw a little ball or something around that point, the fluid wants to go to that point. There's a net inflow overall. Okay? That's the way I remember it anyway. I just think of divergence as measuring spread, expansion or compression. Okay? Okay. So, here it is on the other page. I've summarised it quite nicely, I think, here. Yes, feel free. When we talk about divergence, let me just zoom in. We can think about the spread or the net outflow of a vector field, right? And if the divergence is positive, you've got a tendency to spread, to expand, right? If the divergence is negative, then you've got a tendency to, so if it's positive, there's a net outflow. If it's negative, there's a net inflow. What's in between? If it's negative, you've got a tendency to shrink or compress or something like that. If this divergence is 0, then we say, hey, it's neither expanding nor contracting. Okay? We call this an incompressible state, or an incompressible fluid, really. Now, I do a little bit of research in fluid dynamics when I can, and let me tell you, incompressible fluids are everywhere, right? That's one of the core assumptions of, engineering maths, fluid dynamics, applied mathematics. It's one of the absolute core assumptions, along with things like Navier-Stokes equations, stuff like that. So you'll see it everywhere.
So if we have a function with a positive net overflow, does that mean the gradient in one direction will be greater than one in another one, in the opposite?
Not necessarily. Maybe. So I think maybe do some examples. I'll show you some more examples today. Okay, let's do another example, shall we? Okay, let's do another example. Here, let's just go with this one. Okay? X plus y. So this is, if you want to think about this in terms of i's and j's, it would be xi plus yj. So it's getting a bit more difficult now. Okay? So what does that mean? It means as x and y increase, the length or the magnitude of g is going to increase, right? Let me just show you a little bit about the second part. Okay, I'm just going to draw, say, a circle this time. I'll forget about rectangles and squares and stuff. Okay, so this is the x-axis, this is the y-axis. Okay, if I'm here, where x equals y, right? Let's just say it's the unit circle. So 1, 1. Okay? What is the vector g at that point? It's going to be something like 1 on root 2 I plus 1 on root 2 j. Right? Because I'm on the circle, so x equals 1 on root 2, y equals 1 on root 2. Okay? So let's say this point is the point 1 on root 2, 1 on root 2. That vector there is going to be something like this. Yeah? So what is the vector going to look like? It's going to be pointing that way. What happens if I go over here? Where's the vector for g going to be pointing there? Exactly. Up there. Yeah? Same length? Yeah? What about down here? Here? Okay? Now it's a super simple diagram, but you can kind of see if I'm like a fluid in there, I'm heading out of the circle. I'm not going into the circle, right? We're only flowing from the inside of that circle to the outside of the circle. I'm not going the other way. Would you agree? Yeah. So this is one way to actually justify the conclusion of part 2. Okay? Now alpha. Yeah, look, there's a good question online. Let me put that up. I'd be interested to see if you can draw other rectangles where it doesn't happen, where the conclusion's false. I guess I'm just thinking, you've got the simplest case, put the rectangle at the origin and have, the sides parallel to the axes. But try it. Try it. That's a very good question. You guys are really doing well with the questions today. Other questions? Okay. Yeah. Yes. So divergence.
It's a bit of a dumb one, but can we and would we ever need to calculate the amount that would be flowing outward?
Well, usually, so from an applied maths perspective, we talk about flux, right? So flux is like a fancy word for like flow rate, right? Okay, so you might have, a cylinder filled with fluid and you've got a membrane on top, okay? And you're pushing that fluid through, you want to know how much fluid or the flow rate through the membrane, right? So over time you could work out the volume. Does that make sense? Yeah. Other questions? I'm super excited about this. This is like the highlight of my day. Hey. What do people think at home? Let me know. It may not be the highlight of your day. I apologise for that. All right. So, divergence involves this del operator and the dot product. The answer is a number. It is not a vector. You can interpret the answer as telling you something about the spread or the expansion of your vector field. Okay? Vector fields are hard to draw. Okay? They are much harder than regular functions. Okay? Even in software like GeoGebra, it's still not very good. Okay? Maple's better on one occasion, but it's quite hard to visualize. Okay? Okay, good question from at home. Div G seems to only consider the divergence at a single point. Yeah. So is there a way to calculate it on a region? Yes, that is an excellent question. So for example, if I go back to the document camera, I just take the divergence and I get an expression. That gives you the divergence at any point in space. So you just plug in x, y, z values, you get a number. So it varies as you move around. Okay, so you can do that. Yes. Okay. All right. But wait, there's more. What was the other operation we talked about before? Cross product and scalar triple product. Right? So we looked at cross product in first year. So, you know, we can apply the del operator here to something like this. So cross product is annoying because to compute it by hand takes a bit of work, but the way I do it in my classes is through determinants, okay? So let's say I had a 2 by 2 expression, A, B, C, D, and I put these parallel lines. It's defined as AD minus BC. Okay, so that is the determinant of a 2 by 2 matrix, if you like. Okay? So we are going to use this to compute whatever this curl is. But before we do that, let's try to understand what curl measures. Well, divergence measures spread. Curl, on the other hand, measures rotation. Okay, the tendency of a vector field to rotate or, you know, push things around and rotate them. Okay, highly topical with our cyclone on the way, right? So just like we drew some pictures for divergence, we can also draw pictures for the curl. But let's just compute it and see what happens. Okay? All right. So, part A. Okay, F is that crazy looking vector field. Who knows what it is? But let's just compute it, compute this so-called curl, and we'll have a look at what it means. All right, so this is the way I do cross products. Maybe you do it differently. I write it as a tree by tree determinant. Okay? 3 by 3 determinant. And then the components of the vector come here. So x squared minus y plus z. Okay. Now that's a mess, but how do we expand a 3 by 3 determinant? Well, it depends on the thing I wrote at the top of the page, and then a little game that I like to call cover up. Do you know this? Have you heard of this? Yeah? Okay, so you can do this any way you want. I'll just show you my method. If you think my method's terrible, just feel free to fight the power and do your own thing. Okay? So the way I do it, I start up here and I expand this determinant along the top row. Okay, how do I do that? Well, I go to the first entry and I cover up the row and the column. You stay there. Okay, the row and the column that I is in. And then I multiply I by the determinant of what's left. Okay? So what's the determinant of this? It's d dy of z squared minus x minus d dz of y plus z. Okay, you go diagonally. Okay? And then you move along the top of the determinant. Okay, so you write that down, then you go over to j. Oh, j's in the middle column and the top row. Okay? You multiply j by the determinant of what's left. And then you move on to k. K's in the third column and the top row still. And you multiply k by the determinant of what's left. The only thing that you need to remember with this method is you alternate the sign. So plus I minus j plus k. Okay? Now if you don't want to do it that way and you have your own methods, fine. No problem. So if I was doing it this way, this is what I do. So it's those ones there. Okay, so that's my first bit. Minus j, okay, so you cover up that, cover up the top one, and it's the determinant of what you can see. Okay, lastly, k, cover up those two things, multiply by the determinant of what you can see. Okay, so now you've got, let me just triple check that, yeah. Now you've got 2 by 2 determinants, which you know what to do. You go, hey, I am going to do that on that minus that on that. Okay? All right? So now it gets a bit messy. And there are probably faster ways to do this, but this is very methodical, very, you know. So d dx of y of d dy of that's 0, d dz of that's 1, d dx of that's going to be negative 1, d dz of that's going to be 0, and d dx of that's is 0, d dy of that's negative 1. Okay? Yep. Mm-hmm. Okay? So it's going to be something like negative 1, 1, 1. Okay? So note our answer is, it's not a number, it's a vector. It's a vector. So we don't know what it means yet, but we will find out in a minute. Okay? The hint is it has something to do with rotation. And what does rotation even mean in this vector field sense? Well, that's a good question. Okay, let's take a 10-minute break. Come down if you have questions. Feel free to ask me questions online. And we will finish this off in about 10 minutes, okay? So come on back, y'all. Let's get back to it. Let's get back to it. All right, take a seat. Let's get back to it, people. Oh, someone waited until 3 past to walk out. It's like, I failed. I failed as a teacher. What can I say? That's rough, you know. All right, so just to refresh our memory. In the previous lecture, we talked about divergence. And it involved this dot product with this del operator, and it had to do with spread or compression or expansion. Okay. Then we moved on to this other operator where you've got a cross product involved, okay, called the curl. And we think, at least from the text, that this might have something to do with the rotation of a vector field, okay? So let's pursue this, and let's have a look at part B. Now, last part of question part A is, here's our crazy vector field, compute the curl at this point. So what do you notice about our answer? It's a vector, but does the vector change? It's a constant vector. So it doesn't matter which point we're at, the curl is always the same. Okay, so if I was to finish off this question, it'd be something like, let's call this P or something, right? Curl of F at P is just the same vector. Okay, nothing fancy. All right, part B, which is again far more interesting than part A. Now I must confess, if you look at the practice questions for lab test 1, they're actually like part A. They're not like part B. Okay, but let's try to understand what the curl can measure. All right, so here is our vector field G. So in this case, it's going to be G is yi plus 0j. And I'm again only in 2 dimensions to keep things simple. Okay? So let's try to draw it and see what happens. At least draw it very simply. Okay, so in this setting, G is yi plus 0j. Okay, so what direction will all the vectors, well, if y is positive, what direction will all the vectors be pointing? They'll be all pointing horizontally, right, towards the positive. Oh, hang on, no. I's, they'll be pointing up, won't they? Right? And if y is negative, they'll be pointing down. Hang on. No. See, now I'm getting confused. Right? I vector looks like that. Okay, so if I take any multiple of that, I'm going to be stretching it or flipping it. Oh, God. What are you paying for, hey? All right, so let's say I'm here, and I'm at 2 on the y-axis. So x is 0, y is 2. This vector is going to be 2i. Yeah? If I'm down here, negative 2, this vector is going to be negative 2i. Okay? Can you see what's going to happen already? Right. If I come down here to 1 and negative 1, you're going to get You're going to get similar vectors, but half the length. Okay? All right, so based on that, what does this have to do with rotation? So let me draw in what I call a paddle wheel. It's a very scientific term. It looks like a virus. You can think of those things as having legs or wings or something, right? So if this paddle wheel or virus is in my vector field, what's going to happen to the wheel? It's going to turn, right? It's going to rotate about its center. Okay? It's going to rotate about its center. So if we use that as a rough definition, then we have some idea of curl and rotation, but we haven't calculated the curl yet. So let's calculate the curl. So here we've only got like what I and J, and you know, we don't care about the K. So, but we can still calculate the curl. I'm going to put an extra K in, right? So you can think of this yi plus 0j plus 0k. Okay? And it's going to be y 0, 0. Okay? Now this is an easy one to expand. There's only going to be one sort of output for this, and it's going to involve the k, right? Because if I cover that up, I'm differentiating zeros. If I cover that up, I'm differentiating zeros and y with respect to z. And if I do that, the only non-zero thing is going to be that term there. Okay? So I won't bore you with the details, but you get something like that. Okay? Now, let's just think about the coefficient there. What is the sort of the k component? We can talk about that number as we call it the scalar curl. Usually curl's a vector unless we do something different, right? That's a number. Now that's negative. Which way will our paddle wheel rotate? Clockwise, yeah? Okay? That is a general phenomenon, okay? If this was positive, positive 2, positive 3, whatever, the wheel would rotate the other way. Okay? What do you think if this scalar curl was 0? There's no rotation. So can anybody think of a word that you might know to describe this? Clockwise? No, like we talked about compressible and incompressible vector fields and fluids before. What? Yeah, irrotational. Right? If the scalar curl's 0, you've got what we call an irrotational vector field or an irrotational fluid. Okay? Oh man, this is so good. Questions? I'm sure. Oh, thank you for subscribing. I have subscribed. Thank you. By the way, I've made 1,000 videos. Not once do I say that awful thing to like, share, and subscribe. Not once. I made a deal with myself. I said I'm not going to lose my self-respect, at least not yet. I don't say it once, right? And some of my friends, you know, their kids are on YouTube or TikTok or whatever, and they're sending me videos. Oh, isn't my kid great? And it's like the first thing they say is like, share, and subscribe. It's like share, and subscribe. Oh, and here's my video. It's like stop it.
So the function that we're dealing with was given with respect to 2 dimensions. Is there a reason why we take into account the third one, like all of a sudden?
So we can compute the curl, right? So and 2 dimensions is simpler than 3. You can have 3-dimensional, situations. You can have 3-dimensional situations. It's a nightmare sometimes, though, right? Like even to visualize, or draw, it's a nightmare. So I'm just trying to start with 2, and let's, we build it up from there if we want to. Okay? Again, so people doing fluids, are you seeing stuff like this? Yet? Yeah? Good.
Does the curl vector, does that denote the axis of rotation of the vector field?
Yeah, so yeah, Okay, that's a great question. That's a great question. Okay, where is this vector going to be pointing in relation to there? Yeah, in, right? Exactly. So you can. So it's still consistent. It's still consistent with what you learn in first year. That okay, you got two vectors, you cross them, and you get something normal that points up like that or like that. Okay, great. I didn't think of that. That's brilliant. Yeah, I'm coming. Hello?
So, with the I and the J, if you have a two-dimensional equation like that, can you do the cross product with just I and J, or do you need the K as well?
So you can do it. So see the G, it says G equals yi circle plus 0j. You would just be sneaky and say, hey, let's consider this in 3D. And I'll just put plus 0k. You with me? Yeah. Because dimension's important, right? We want to make sure that we don't sort of mix up our dimensions. So you can always consider 2 dimensions sitting in 3 dimensions. That's fine. Yeah. Yes.
Could you please explain where the -1 comes from and what scalar curl means?
Yep. Well, I'm defining scalar curl to be whatever the number is next to k. Okay? So let's do the computation again. We play cover up. Okay? So, start along the top row. I is in the top row and the first column. Multiply I by the determinant of what's left. What's the determinant of what's left? 0. Okay, so now we move. J is in the middle column and the top row. What is the determinant of what's left? 0. And finally, get onto K. d dx of 0 minus d dy of 1. That's where the -1 comes from. Okay, and I'm saying, right, it's always going to be just only k's for these 2D, like these simple 2D vector fields. Is there something special about that coefficient of k?
Okay, and what if like another value was not 0? Then what would your scalar curl?
You wouldn't. You wouldn't get, or you might get like a x or a. So this thing doesn't have to be a constant. It could depend on x and y. But here it's just so simple that it is. Okay, but it doesn't have to be a constant. Yeah. Yes. I'm getting my steps up. My fat bit's going over time.
Is it influenced by x or y, or is it defined to be just whatever is in k?
No, yeah. So this value is not. This is a constant, -1. But in the general case, it can depend on position. So x and y. Isn't that what you're asking? So this one doesn't depend on x and y, right? The scalar curl in this case is just a constant everywhere. But in more general problems, the coefficient of k could depend on x and y. So as you move around, that scalar curl value will change. Does that make sense? Okay. All right, so negative value, clockwise rotation. This is a general thing. Negative scalar curl, clockwise rotation. Positive, anti-clockwise rotation. Okay? Overall, the curl measures the tendency of the vector field to rotate things, I guess, things. Okay, finally, like you said before, if you have 0 curl, you talk about irrotational. Vector field being irrotational. Now, some of you may be thinking, well, hang on. This doesn't look like, it's just pointing in two opposite directions. How does that rotate things? Well, the field may not be rotating itself, but its impact will rotate stuff, okay? Questions? Yes, hang on. Now again, would you see something like this in the lab test, where you've got to draw pictures? No. Could you possibly see this in the final exam? Yeah, because it's more conceptual. The final exam is going to be more conceptual.
Is in physics we have like the right hand rule? Would that be like an example of like a scalar curl?
Yeah, it's good idea. So let's talk about right-hand rules. Mm-hmm. Oh, it can be both, but yeah. What? You want to say?
You can also represent torque with it. Yes, you can. Yeah, you can also represent torque, so I guess it's spinning the wheel. Yeah. So if the K value is representing the direction, does the I and the J represent the center of the pinwheel?
Doesn't have, I mean, they can exist irrespective of that. But I guess what point you're at, which you can describe using I's and J's.
Okay.
So if you move around your plane or whatever, the vector field will change. But to get to that point, you can use I's and J's. Right? Okay. These are great questions. Okay. All right, let's look at the last one. Here's another example. Our old friend from before, xi plus yj. Okay. Show that if you calculate the curl of that, you get 0. Right, I won't do that for you, but let's just draw a picture. Okay, and I'm here, let's say, and my thing's going to go. So these are the G vectors. Okay, and let's say I draw in my little paddle wheel. Do you think it's going to rotate the paddle wheel? No. Okay. It's sort of normal to and parallel to all the I don't know, the legs or the teeth or whatever it is. Okay. So vector fields are hard. I'm not going to lie about it. Vector fields are hard because they're hard to process in your brain. Okay? But if you can do some things and you can draw simple pictures, then you can at least understand their effect or some special cases associated with them, right?
It's not so essentially, roughly to sum up, if the total if you put something in and it would theoretically rotate around the center, then that would be the total scalar curl. If it can't, that means it's 0.
Yeah, loosely speaking. So I look at it as if there's positive or negative, you'll get some rotation. If it's 0, there'll be no rotation. Yeah.
So I saw in like part A, there's also I and J, right? What does those represent, or we just don't really care?
Well, part F?
No, so like earlier, when we are on like the earlier question F, there's also, for calculating curl, there's I and J as well. Does it represent?
So let me have a look. Yeah? Yeah, it's not a special vector field. I just made it up. Okay, it's just like a toy one. Yeah. Yeah. This is so bad. I'm so sorry that it's not working.
So would the I mean something if we had a vector field that would rotate around the x-axis or something? And then, like, for the y-axis, then j would mean something, etc.
Yeah, exactly, exactly. So depending on where you're looking, yes. So I think you can bring meaning to that. Okay. All right. So that's divergence. That's curl, and that's kind of what it means in a loose sense. Okay. The most important thing from a lab test perspective: calculate them. Calculate them. Now, somebody was talking about scalar triple product. Who was that? Yeah. So, can you combine these things? Yes, you can. Right? How about this? Boom. So what? So how would you pronounce that? Div curl F. Huh? So you take the curl, you get a vector, and you take the divergence of that vector. Oh my God. What about this? What about this? Okay. So phi is not a vector. It's just a regular function of two variables or three variables. What would you make of that? What would you call it even? Huh? Yeah, or div grad? Div grad, div del's fine. Div grad, even better, right? What about this? Div F? Div. Does it even make sense? The first question is, does it even make sense? So if not, why not? Yeah. So this gives you a number or a scalar, and then you're dotting it with a vector. That doesn't make sense. Okay? So be careful about these things because sometimes the operations work and sometimes they don't. And it goes back to what I was saying before. When you're given some information in the test, look at it very carefully, right? Because it's easy to get confused. It's very easy to get confused. Okay? What about this one? Hang on, let me put the air conditioning back on. Start. Okay, what about this one? Oh, how would you pronounce that? Anyone? Curl curl? Curl curl F? Huh? Does it make sense? Let's think about it. Okay, that's going to be a vector. Can I cross something with a vector? Yes. So it's like the rotation of the rotation. We're getting a bit abstract now. Okay? All right. Okay. is the last thing we'll do today. Line integrals. Now, line integrals is probably the last thing you'll see on lab test 1. It's like the limit up to and including line integrals. Okay? So, let's think about it. Go back to high school physics. Okay? You want to you've got a force and you're applying it to, I don't know, some mass, and you move the mass, right? And you want to calculate the work done. Yeah? Okay, and it moves in a straight line and everything's neat and nice and, yeah? Remember those sort of questions? Okay. We can use this to answer problems like that where the movement is over a curve. So it doesn't, I don't know, I'll move this, right? Straight line. But what happens if it was like this, like that? Okay, that's my great demonstration. Okay? That's one of the typical connections with these line integrals, okay? So where does the word line come from in this context? Well, I'm glad you asked. So let me draw you a picture. The standard way we do things with sort of high school calculus is we integrate over an interval. So from A to B. Yeah? And we get the area under the curve or whatever. Okay? So we're integrating over an interval. So what happens if I curve that interval into, I don't know, a graph or a curve or something like that? So instead of having this straight line segment, here, I want to integrate over something like that. So that's not the function, that's the domain that we're integrating over. Okay? Is it possible? Yes. Let me show you an example. Suppose I've got a function like that and the unit circle. Okay? Let me show you a picture. Come on. You going to open for me now? Yeah. Okay. All right. So, the plane is basically z equals x plus y in the original question. Okay? So, you start off with the plane. Okay? The circle, the unit circle, so x squared plus y squared equals 1, so a center 0, 0, radius 1. Let's smash that plane with the circle in 3 dimensions. Okay? All right. Now, if I look very closely, there's a line or a curve of intersection. Yeah? So let's do that. There it is. Okay? And what's happening in the xy plane? Okay? So, what our aim to do here is we're going to integrate over a curve. Okay? It sort of looks like this. Right? Looks like a bit like a fingernail. So this bit here. Okay, and that's actually curved in several dimensions. Okay? So how can we even do that? Well, let's look in the xy plane and describe the circle. How do we do that? Cos t, sin t, something like that. Okay? So there's a bit sticking up and there's a bit sticking down. Okay? So, who can tell me? What do you, just from the picture, what do you think the total area is going to be. So you've got two curved walls, one above the xy plane and one below the xy plane. What do you think that the result's going to be here if we do some sort of integration? 0. Okay, so if you look here and you apply the area, the idea of area, that little bit, like a fingernail, give you a positive area. That bit there underneath will give you a negative area, and there's symmetry. Okay? So, first of all, let's get to what these things actually mean. Okay? Note the notation. You've got a couple of things. You've got a DS, so nobody really knows what that is. You've got a C, then you've got an F. At least we know what the F is. C is the unit circle with center at the origin, and we're doing some sort of integration. Okay? So if I'm drawing a picture, which I like to do, I'd go something like this. Yep. And to get onto that circle and move around, I'm going to have this parameterization, some vector function of one variable. Okay? But it still doesn't tell you what this thing means. It's shorthand for the following. Okay? So that first integral is just a quick way of writing this mess. But let's look at this mess for a minute, because it actually, it's just year 12 or year 11 integral here. Okay? You've got a function of one variable, t, and you're integrating with respect to t from t equals a to t equals b. Okay? So how does this work? Let's look at our example again. Here is our curve, and let's describe our circle using x equals cosine t, y equals sine t. And I want to push out the whole circle so t can go between 0 and 2 pi. Okay, so we've got that. Let's use this mess and see what happens. Okay? Let's use this mess and see what happens. So, f along the curve. So if this is x and that's y, I just put them up here. Okay? Next thing, the derivative. And we take the length of the derivative. So we differentiate this with respect to t. So cos goes to negative sine. Sine goes to cosine. Now, what's the length of that derivative going to be? 1, right? Cos squared plus sine squared, you can use that. Which is nice because we get rid of the crazy square roots. Okay, that's all we need. That bit, multiply them together and integrate. It's not that hard, right? So I'll go from not a to b, I'll go from 0 to 2 pi, because that's where it is. Okay, so now it's just standard integration. Okay? So, You can use symmetry there, or you can use the picture. The areas cancel each other out. Okay, but we've got a number. We can relate it loosely with area. And the way we compute it is through this parameterization, this R vector function. Okay. Questions? Questions? Now, not all line integrals are like this, but they're the basis. You can see in part B there's sort of slightly different notation. Okay? Okay, so this is one line integral, and it gives us area of a fence or a wall or something like that, a curved wall maybe. Oh, yeah. Yeah, is that what you're going to say? It's like a curved wall. Yeah. So let me put the picture back up because I think it's a good point. Okay, so it's quite hard to picture. Thank goodness for GeoGebra, right? So let's start again. We've got our plane. We smash it with the cylinder associated with our circle. Okay, you've got an intersection there, and in the XY plane, you've got that going on. So you integrate around that, and the area will be below that curve and sort of a curved wall. Right? And there's also a negative part. So when you add them together, they cancel each other out. But again, what would you be asked to do in lab test 2? You'd be asked to just do the computation. Okay? So the hardest thing is parameterizing. Okay, that's probably the hardest thing. So let me just put that up for everyone at home. It's the parameterization. How do I get good at that? Well, do lots of problems. Okay, a circle's easy, a line segment's easy. Okay, we wouldn't ask you anything really shockingly difficult. Okay, now what's happening in the second one? Again, I'm glad you asked. This is where you've got a vector field, not a scalar field. It is the following. Note that there is a dot product there. Okay? So we're not interested in lengths like the first one. We're interested in a dot product. And the question is why? Well, we have to sort of deal with the vector field somehow. And there is a geometric interpretation, but that's the sort of the computational thing we'll be using. Okay, so this is important. This is even more important. Okay, because that's pretty much what you're going to get tested on. Okay. So how do you do this? Well, it's very similar to the previous problem. Let me just show you. So this is part A, part B. All right. So the vector field, which is this mess, along our parameterization. So x equals cosine t, y equals sine t. So replace those x's and y's with those things. Okay, so x equals cosine t, y equals sine t. Okay? Now we've already got the derivative, it's there. So let's take the cross product, the dot product, and we'll get something involving t. Okay, so we do that, we're going to get sine squared and cos squared, which is going to be 1, and we're going to get a negative sine t. So 1 minus sine t. then we simply integrate that from 0 to 2 pi. Okay, and if you do that again, you get a number. Now it's not clear if this has anything to do with area or anything like that, because we're dealing with vector fields here, not just nice curves. But we will understand that a bit better in a moment, or maybe in the next lecture. Okay, but at the moment, just the machinations, the ways of computing these things. Questions? Questions? Yes.
Is there a reason the parameterization formula for the vector field is not in the notes? Because like in the notes, we have the formula in terms of unit tension.
Yeah. So this will, like on the next page, this gives you a way of interpreting what you're calculating. This is the way to actually calculate and solve a problem. Okay? So if you look on the next slide, you're like, oh, what's this? What's this T hat and all that sort of stuff? I'll show you what that means in a minute, right? But this and this, from a computational point of view, is what you use to solve problems, right? That's pretty much the difference. Does that make sense? So on the other page, we look at tangent vectors and geometry and that sort of stuff. Here, we're just doing the problem. Okay? More questions? Notice we get numbers for both of our answers, not vectors, numbers. Okay, as you would expect for a dot, something with a dot in it, dot product. Yeah? More questions? All right. Let's spend the next 9 minutes having consultation. Come on down. Ask your questions online if you have any. Thanks for staying with us. Good luck. Don't get blown away in the next few days. Hope to see you tomorrow morning. And just enjoy.